Physicists from the Department of Nanophotonics and Metamaterials of ITMO St. Petersburg, Russia, have experimentally demonstrated the feasibility of designing an optical analog of a transistor based on a single silicon nanoparticle. By drastically changing the transient dielectric permittivity of the material, they were able to alter its scattering diagram, even up to 20% tuning of reflectance as demonstrated in their experiments. Because transistors are some of the most fundamental components of computing circuits, the results of the study have crucial importance for the development of optical computers, where transistors must be very small and ultra-fast at the same time. As Moore's law becomes less and less sustainable due to quantum effects that can no longer be deemed negligible in the nanoscale, it seems that performance can no longer be developed through quantity, and instead must shift towards the development of better quality transistors. Faster switching, better stability to heat changes, and smaller in size. These are all properties of the set ideal transistor. Silicon nanoparticles have been a popular focus of similar studies on optical transistors. What's so special about what these guys did is the clever design which they approached the experiment with. The team found that they can dramatically change the properties of a silicon nanoparticle by irradiating it with intense and ultra-short laser pulses. The laser acts as a control beam, providing ultra-fast photoexcitation of dense and rapidly recombining electron-hole plasma, drastically changing the dielectric permittivity of silicon for a few picoseconds. This allows manipulation by both electric and magnetic nanoparticle responses, resulting in dramatic changes of its scattering diagram and scattering cross-section. For instance, the direction of nanoparticle scattering can be changed from backward to forward on picosecond timescale, depending on the wavelength and intensity of the incident control laser pulse, as shown in the results of the experiment wherein we can see different models of scattering as the wavelength is changed. This concept of ultra-fast switching is very promising for designing of all optical transistor. As the field of data communications transitions towards more developed optic fibers, optical transistors could potentially eradicate the second half of the problem. That is, the bottlenecking of data, which happens due to the fact that current optic fiber methods still pass information through source and sink computers, which are still sufficiently limited by electron signal carriers. We could also improve circuitry performance in countries with a more higher than average temperature. With daily temperature conditions that exceed the working condition temperature of a device, transitioning to a component that has a more stable response to temperature would mean higher performance. There have been a lot of approaches in creating an optical transistor, and surely more will be developed in the coming years. But it stands that the tuning of the dielectric permittivity of a single dielectric nanoparticle by a photoexcitation of dense electron-hole plasma opens a novel class of ultra-compact nanodevices with potentially ultra-fast timescale based on the diversity of magnetic light effects.